I'm Noé de Rancourt from the University of Lille. I was a former student of Stevo in Paris. And the title of my talk is Big Ramsey degrees of metric structures, as you can see. It's a joint work with Tristan Bice, Jan Hobyczka, and Maciej Koneczny. So it's about basically, I don't know if you know big Ramsey degrees. I guess not everybody does, at least. Yeah, so I will explain, don't worry. Big Ramsey degrees is a part of structural Ramsey theory, where we try to prove Ramsey theorems in specific structures, usually finite or countable, sometimes graphs, partial orders, vector spaces, etc. Don't know if you know a lot about this. And big Ramsey degrees arise when you try to give a version of the infinite Ramsey theorem in those structures. In many cases, you can't. You can in way less cases than for the finite Ramsey theorem, actually. And but in those cases, you can still prove a result, which is kind of a restricted Ramsey result, where you only reduce to a given number of colors, and this number is an invariant of the structure and is called the big Ramsey degree. And well, this theory is well developed for discrete structures, like discrete countable structures, but for plenty of reasons, we wanted to try to adapt it to deal with metric structures. So typically, separable metric spaces and separable Banach spaces. I guess there could be also other types of structure where it could apply, I don't know. Yeah, and there are several motivations for that. There are motivations coming from dynamics. There are motivations coming from Banach space theory. And it was a question, like, the question was raised in the Kekris-Pestov-Sorachevich paper, if you know about it. And actually, yeah, so we are trying to prove results for metric structures, but not only. Something that was not even clear at the beginning what is the right notion for metric structures? Well, we didn't know. We managed to find one good candidate that works for many structures, and that's what I would like to present you today. But first of all, so that you understand, let's start with the discrete setting. Basically, to remind you what is a big Ramsey degree. So the discrete setting, all of you know the infinite Ramsey theorem, I guess, yeah. If someone doesn't, I can restate it. So a question is, if you consider the structure Q with its standard ordering, can you prove an analog, a structural analog of the infinite Ramsey theorem in it? And I will try to ask the question in a bit more precise terms, because this can mean a lot. So the question, well, that has been solved long ago, and I will give the answer. But the question is, given a coloring C of Q, let's say D element subsets of Q, with k colors, with a finite number of colors, does there exist a subcopy of Q monochromatic? So let's say such that x to the d is monochromatic. So what is this? This is the set of isomorphic subcopies of Q inside itself. And here Q is just embedded, is just endowed with the order, nothing else, no operations. And of course, like, the answer would be obviously yes if you don't even require the order. because it's just the Ramsey theorem, right? A copy of Q in itself without the order is just a countable set, and that's exactly what the infinite Ramsey theorem tells you. But with the order, the situation is different. You add more structures. This is why it's called structural Ramsey theory. And so what about the answer? Well, for d equals 1, it's very easy to see that the answer is yes. Reason, if you color with, let's say you want to color with two colors, to get finitely many colors, you just iterate this. You want to color with two colors, well, either there is a blue interval, an interval which is entirely blue, then this interval contains a subcopy. Or there is no interval which is entirely blue, which means that the subset made of red points is a dense linear order, so it is isomorphic to Q. Now, what happens for d equals 2? Well, for d equals 2, the answer is no. And there is a very simple coloring with two colors that shows this. Is due to Sierpinski in 1933. So what do? You consider, let's say, this is a different ordering. I hope you can recognize this from the usual one. I will put well ordering on Q. And I will color a pair XY in blue if, let's say, the two orders agree on this pair. And you color it in red otherwise. And what does happen? Well, if you consider a monochromatic subset of this, that on this whole set, the two orders will agree. And meaning that they agree implies that in particular the standard order of Q will be either a well ordering or a reversed well ordering. And an ordering or a reversed well ordering cannot contain a copy of Q, of course. So every copy of Q will meet both colors. Well, you have this. Can you now do the same with three colors, for instance? Well, the answer is no. So the result has first been proved by Galvin. It is an unpublished theorem, but I think it was probably in the 70s, I would say. Galvin proved that for every coloring of Q squared with finitely many colors, there exists a subcopy of Q in itself, such that pairs of X meet at most two colors. You cannot do worse than that. Whatever other coloring you choose, you can reduce it to two colors. We say that 2 is the big Ramsey degree of pairs in Q. So to state further results, I will introduce a partition relation. I will write, let's say, that A, B, C are structures like first order structures in the same language. Oh, am I allowed to write on this one?
Yes.
Yeah, you turn the camera, okay. In the same language. And I will write C arrows B A K L where K and L are integers, if for every coloring of embeddings of A into C, so embeddings in the model theoretical sense, there exists a B prime subcopy of B in C, such that if you just look at embeddings that arrive in B prime, you're monochromatic. Such that you're not monochromatic. Sorry. Oh, I forgot to say the number of colors. K colors. This K is for the number of colors. So for every coloring of EMB-AC with K colors, there exists a B prime copy of B in C, such that on the embeddings of A into B prime, C attains at most L colors. And actually, if I want to rephrase this statement by Galvin, you can rephrase it by saying that Q arrows Q2, so here 2, you see it as an ordinal, so an ordered set, K2. So actually, for every K, you have this partition relation. Because what your colorings...
Don't you want the 2 on top to be arbitrary, some other L?
What?
Don't you want the 2 on top to be some other, I mean, you're partitioning pairs.
Yes.
Which is trivial version of Shapinsky. So you want, I mean, the non-trivial version is if L is bigger than 2, right?
Is L, so, sorry, L is the number of colored...
No, sorry, not L, but that upper index.
This one?
Yeah, I mean...
It's absolutely not trivial, it's a difficult proof. But, like maybe what you say is that what is trivial is what...
I see, the color, yes, no, you're right.
You understand what I mean?
Yeah.
Okay. Yeah, okay.
But in fact, what you stated is even stronger. You can change the 2 to an arbitrary number.
If I change this one to an arbitrary number, I don't have 2 anymore here.
Yes,
I will say it just after. It was for the example,
yes, okay.
But I will state it just after. So yes, this one means that Q arrows Q2 K2 because if you color embeddings of an order set with 2 elements in Q, which are exactly in bijection with pairs of Q, then you will be able to find a subcopy on Q on which this is monochromatic. So actually, what I was about to say is exactly that indeed, if you color more than just pairs, you can do better. So the theorem, which was originally proved by Lever, unpublished, and then improved by Devlin in 1979, is the following. For every D, so which is the size of the tuples you color, there exists some number TD, which is also a natural number, such that for every number of colors, Q arrows Q D, TD, and K and TD. So if you color D tuples, like D element subsets, with any arbitrary number of colors, you can always reduce to a fixed number of colors, which is TD. And actually, so Lever proved the existence of the TDs. Devlin computed them. Well, I will give you the formula because it's funny. Yeah, so the computed the minimal ones. So let's say minimal TD computed by Devlin. TD is the value at 0 of the 2d minus 1th derivative of the tangent function. So I say it like that because it's funny, but actually it's a much more concrete number. So this theorem is proved by giving a tree representation of Q and using Millikan's tree theorem, which is a Ramsey theorem on trees. And this is a function that counts a certain number of finite trees in certain families, basically. So this is how it works. And so, yeah, you've done that on Q. You can do that for plenty of other structures. Let me check that I forget nothing. Yeah, so more generally, definition. Let's say that X is a countable structure and A is in the edge of X, so it's a finite. Let's say, anyways, if I start to consider languages that are not relational, I will make mistake. So imagine that in my talk, every language is finite and relational. Plenty of things expand to functional languages, but so I don't make mistake, it's the set of finite substructures of X here. We say that A has finite big Ramsey degree. I will maybe spell it out entirely for the first time. Big Ramsey degree in your X if exactly the same holds for every, no, not for every D, if there exists some T such that for every K, X arrows X A K T, so you can always reduce a coloring of embeddings of A into X to at most T colors. And in this case, the big Ramsey degree is the smallest such T. Is the big Ramsey degree denoted by BRD of A in X. So to make the link with simple things that all of you know, let's spell out the infinite Ramsey theorem in it. So the infinite Ramsey theorem tells you that the BRD of n with the order seen as an ordered set in omega seen as an ordered set is equal to 1 for every. So because here what you color are embeddings like increasing maps from n to omega, which correspond bijectively to subsets of n of omega. Sorry. And so the big Ramsey degree is 1 because you can always reduce to one color. You cannot remove the ordering because if you remove the ordering, then you don't have this bijective correspondence between subcopies and embeddings anymore. If you have one subcopy, you have plenty of embeddings which correspond to each permutation. So it's pretty easy actually that to prove that you can reduce to one color per permutation. So you get that the BRD of n in omega, so n without structure, omega without structure, is factorial of n. If you're asking yourself why I'm coloring embeddings and not subcopies, well, it's just that when you go further in the theory, for plenty of reasons, it's usually better, it's usually more practical, and in particular to present you the metric results that I will give you later in this talk, it will be simpler to have this formalism of embeddings. But what you need to know is that it doesn't make a big difference because it's easy to prove that if you have big Ramsey degrees for substructures, and you have infinite. If you have finite big Ramsey degrees for substructure, you have it also for embeddings, and this is actually an equivalence. And computing one from the other, it's not very difficult, exactly like this. So basically, it's the same. Okay. I think, yeah, maybe I should give you one last definition. So definition, we say that X, a structure X, is indivisible if, exactly as when you color elements of Q, for every coloring of X to a finite number of colors, there is a monochromatic, let's say, Y subcopy of X, and this is equivalent to say that the BRD of singletons in X, this is just a singleton, is equal itself to 1. Is equal to 1. So indivisibility, like you have for Q, is a particular case, is the simplest particular, the best particular case of a big Ramsey degree result when you color elements of the structure. Well, so you can do that for the structures. Q was the first historical example, but there have been plenty of other examples, which took a bit of time to arrive, actually. So there was the computation of the big Ramsey degrees of the radiograph. If you don't know what is the radiograph, it's it's the Freyse limit of the class of all finite graphs. If you don't know what is a Freyse limit, let's just tell yourself that it's a very big graph, a very complex countable graph. This dates from 2006, computed by Laflamme, Zauer, Vuksanovic. And then it took a bit of time for other results to arrive. And there have been very recent new methods. Recent means from after I defended my PhD thesis, which is not that recent, which is not necessarily that recent after all, but like from less than 10 years ago. On one hand, there have been methods developed by Natasha Dobrinen. On the other hand, by Jan Rubiczka, who is my co-author. And from, let's say, from 2020, a whole lot of new examples, of new computations of big Ramsey degrees have been produced. So, for instance, the first example by Natasha Dobrinen was big Ramsey degrees of the Freyse limit of all finite graphs without triangles. And before going further, before leaving the finite case, the discrete case, I will give you a little bit more of details on the Sierpinski coloring and on this kind of colorings, because it will be pretty useful for the way we will define big Ramsey degrees in the metric case. So remember this Sierpinski coloring, let's call it CS, from pairs of elements of Q to 2. It has two properties. So the first property is that it is unavoidable that is, on every subcopy, it meets all the colors. So for every X subcopy of Q, C is still surjective on pairs of elements of X. So this is what the argument I just gave earlier. But actually, the argument of Galvin for proving that you can always reduce every coloring to 2 colors shows a little bit better than that. It shows that actually, if you consider any other coloring, you can, in some sense, always reduce it to this one. So for every other coloring from, let's say, pairs of elements of Q to any finite number of colors, there exists some subcopy such that if you work in this subcopy, look, maybe I will put myself here, you will see better, such that if I work in this subcopy, here I have my Sierpinski coloring with 2 colors, here I have my arbitrary coloring with k colors. Well, on this subcopy, you can factor this one through this one. So there exists F from 2 to k such that this diagram commutes. So in some sense, this Sierpinski coloring is the worst coloring ever, and every other coloring can be reduced to this one. So you have, at the same time, a limitation to what Ramsey results you can get, and you have an optimal Ramsey theorem above this limitation. We'll say that this CS is a big Ramsey coloring. And this is not at all an isolated fact. This is not a coincidence. Because, well, of course, having a big Ramsey coloring with a certain number of colors implies that this number of colors is the big Ramsey degree. Unavoidability shows you that the big Ramsey degree cannot be below it, and universality can show that you can always reduce to this number of colors, so it gives you an upper bound. So finally, big Ramsey colorings, when they exist, characterize big Ramsey degree, but actually as soon as you have big Ramsey degrees, those colorings exist. So more generally, if T is the big Ramsey degree of A in X, then there exists C from M of A into X with T colors, a big Ramsey coloring. This is an elementary result. This can be proved completely abstractly. And this is another way, actually, this is an equivalent way to define a big Ramsey degree. So now, I think we have everything we need. I will expose you some motivations for passing to the metric case. There are plenty of motivations, but I have some time, so I will give you a good idea. Who among you is familiar with the Kekris-Pestov-Todorchevich correspondence? One person, so okay, I will give a short overview. So, let's say that, just to be sure everybody is okay with that, X is ultra homogeneous. If every isomorphism between finite substructures of X extends to an automorphism of X. So this is the case of Q, for instance, for the order. This is the case of the radiograph I told you about for the graphs. And, well, there is something pretty nice that happens when you have a countable homogeneous structure. We have this very important correspondence. So the Kechris Pestov Todorchevich correspondence, which was a very important paper in 2005, which in some sense restarted interest in structural Ramsey theory. They proved that if X is countable ultra-homogeneous, then the following are equivalent. First of all, the age of X has what we call the Ramsey property, which means basically that if you take structures from the age of X, you have an analog of the finite Ramsey theorem, not the infinite, but the finite one. So if I want to spell it out, it will mean that for every A and B in the age of X, for every number of colors K, there exists some C in the age of X, such that if you color the embeddings of A into C, then you will be able to find a monochromatic copy of B, so monochromatic with one colors. So in the case where X is for example, Q with the order, then the age is just the set of finite ordered sets. And so you get exactly, this is exactly the Ramsey theorem. This is the finite Ramsey theorem. This is true. And so what is it equivalent to? It is equivalent to that, to the fact that the group of automorphisms of X, the automorphism group of X with the pointwise topology, or if you prefer the product topology, when you consider it as a subset of X to the X, is extremely amenable so this is a very big, how to say, strengthening of amenability. If every continuous action I mean, this means oh, nice that you could come finally. I did read your email in the bus, but I could not answer because it was not very practical from my phone.
Well, I'll try to catch up.
Yeah, I think you know most of what I said probably. We'll see.
Good.
I recalled what were big Ramsey degrees in the discrete setting.
Okay.
So yeah, so I was saying that saying that a group is extremely amenable means that every continuous action of this group on a compact Hausdorff space has a fixed point. This is a very strong property that you can define for every topological group formally, not only automorphism groups, but it happens that no locally compact group has this property. This is only a property of non-locally compact groups, and actually, I would say that this Kekri-Pestov-Torachevich correspondence is one of the two main methods to exhibit extremely amenable groups. So you can do actually better with this correspondence. As well as in some structures, you don't have an analog of the infinite Ramsey theorem and you have big Ramsey degrees. In some structures, you don't have analogs of the finite Ramsey theorem and you have what we call small Ramsey degrees. And when you have small Ramsey degrees, you can use it to compute to characterize a very important topological dynamical invariant of your group of automorphisms. So maybe I won't enter into details, but or I could give a definition after all I have time. Let's say that a minimal flow of a topological group G is a continuous action from G on K, where K is compact Hausdorff. With no non-trivial subflow, with no subflow actually, with no non-trivial subflow. So a flow actually is just a continuous action on a compact. A subflow is a continuous action on a subcompact. And minimal flow is a flow without a continuous subflow other than itself and the empty flow. And there is a theorem by Alice which say that for every G, there is a unique, what we call universal minimal flow. Of G, and a universal minimal flow is a flow that surjects on every, a minimal flow that surjects on every other minimal flow. So since every flow has a minimal flow, and since this guy is the maximal one for surjection, like surjection that are compatible with the action of the group, in some sense, this flow allows you to understanding this flow allows you to understand the whole dynamics of the group, the whole topological dynamics on the group. And this thing is built by completely unconstructive ways. In most cases, this is, like for instance, for all locally compact groups, this is non-metrizable. But there are some very specific cases where it is metrizable and where you can understand it. It's in the case of automorphism groups. So actually, your first example is when your group is extremely amenable. Where your group is extremely amenable, then the unique minimal flow is just a singleton, because every flow has a singleton as a subflow. So the universal minimal flow is a singleton. So the universal minimal flow of G is a singleton if and only if G is extremely amenable. But actually, even in some cases where G is not extremely amenable, you can have an explicit description of this guy. And one of the ways to get this is using this theorem, which is a consequence of Zekre-Pestov-Todorchevich. So I will give it three attributions because it is obtained by combining the results of 3 successive papers. So first, Zekre-Pestov-Todorchevich, 2005. Then Reinventé, uh, 13, and then Zucker 16, which tells you that for X countable ultra-homogeneous, the following are equivalent. So first, the automorphism group of X has a metrizable universal minimal flow. And second, the age of X has finite small Ramsey degrees which are the analogs of the finite Ramsey theorem. So in other words, for every A in the age of X, there exists some small Ramsey degree of A, which is a certain number of colors, such that for every B and for every K, there exists C, such that C arrows B, A, K, S, R, D of A. So it's exactly as for big Ramsey degrees. You can do as for the finite Ramsey theorem, but you can always only reduce to a fixed finite number of colors that only depends on A. And so actually, even by this theorem, if you have a description in some sense of the small Ramsey degrees, you can describe the universal minimal flow, and this has been done in plenty of cases. Now there is an analog of this proved by Zucker later for big Ramsey degrees involving another kind of flow, which is the completion flow. So this one would be a bit too long to introduce. I don't want to enter into the topological details, but I can state you the theorem. So it's Zucker in 19. For X countable ultra-homogeneous, the following are equivalent. Oh, no, wait. No, the problem with this theorem is that there are still some things that are not completely understood with big Ramsey degrees, and so it's only a partial analog of this one. You only have one implication. I think I prefer not to tell wrong things, so I will only give you one implication. So if X has finite big Ramsey degrees, then the automorphism group of X has a unique universal completion flow. For those who know what I mean, the universal completion flow is kinda the analog of the universal minimal flow, where you replace the Samuel compactification with the completion of your group. So it's sometimes in some way similar, but the problem is that this universal completion flow, for now we don't know if it exists for all groups, and we don't know if it is unique for all groups. And actually, this is the only case where we know that we have uniqueness and existence, and where we are able to actually compute it. So big Ramsey degrees are the only way to approach that. Well, but the point is that there are plenty of interesting metric structures now, metric spaces, Banach spaces, etc., which are analogs of what I wanted to say, which are good analogs of, which satisfy the analogs of ultra-homogeneity in the metric sense. So you need to add some epsilon, but whatever. And for which, well, you can consider their isometry group, and you can want to know whether it is extremely amenable, if it has a universal minimal flow, if it has a universal completion flow, etc. And actually, this part of the correspondence for small Ramsey degrees has been applied to some metric structures. So for instance, let's consider one example, the Urisohn sphere. By definition, the Urisohn sphere S is the unique complete separable metric space of diameter 1, such that, first of all, every finite metric space of diameter at most 1 embeds in it, embeds isometrically, so there exists an isometric subcopy. And second, which is ultra-homogeneous. So exactly in the same sense as before, if you consider two finite structures and an isometry between them, then you can extend this isometry to a non-two isometry of the whole Urisohn sphere S. So in the right setting, this guy is the Fraisse limit of the class of all finite metric spaces of diameter at most 1. And, well, theorem by Pestov. I forgot to check the date, but I think it's probably 98, something like that. The isometry group of S with the pointwise convergence topology is extremely amenable. This has first been proved by Pestov using methods of concentration of measure. Yeah?
You mean S there, or?
S, yes. So this first had been proved by Pestov by using concentration of measure, which is the main other technique to prove extreme amenability. And then this has been reproved using Ramsey properties by Kekris, Pestov, and Torocevich. Another example are the Gourari space, which is a separable Banach space, the Freise limit of the class of all finite dimensional Banach spaces. Its isometry group, like linear isometry groups, is extremely amenable. So this has been proved by Bartoshova, Lopez, Abad, Lupini, Bombo in 2020. And so this is a continuous structure. And for this, they use the Ramsey property and they use the Kukrist-Pestov-Sorolchevich correspondence in a metric way. And this is the only way that is known to do it. There is another example, which is the Poulsen simplex, which is a certain simplex. I don't know a lot about it, but same. It has been proved that its automorphism group has metrizable universal minimal flow. This has been proved by the same people as here in the same paper. And actually, for this, they use a structural analog, a metric analog of this correspondence. So they use, in some sense, implicitly, small Ramsey degrees in the metric setting. So something that that one could ask ourselves legitimately is whether, for instance, the universal completion flow of all of those groups exists and is or not metrizable. And for this, we would need some analog of big Ramsey degrees in the metric setting. Well, we are lucky on one point. I told you that the most precise notion of the most precise case of big Ramsey degrees is indivisibility, when the big Ramsey degree is equal to 1, and it happens to such results happen to already exist before us in the metric setting, and I can show you some examples of those results. So in the metric setting, those results of indivisibility are called oscillation stability. I will show you after why they are indivisibility results, but let me state them first. So I will say that a function chi from x to y, where y is a metric space. So if I have a function like that, I will define its oscillation. The oscillation of chi is the supremum for x and x prime in x of the distance between their images. So in other words, this is the diameter of the range of chi, and so the closer it is to 0, the closer this function is metrically from a constant. And well, we have the following theorem by Gowers in 92. It concerns the Banach space C0. Do you all know what C0 is? Yeah? Okay, you know what C0 is. Perfect. If you don't tell me, I can redefine it quickly. You have a problem with something I wrote earlier?
This is the definition of a diameter.
Yeah.
It's the diameter of the image.
The diameter of the range. This is called the oscillation.
Okay.
Yeah, I forgot to write it, but this is called the oscillation. So, theorem by Gowers, if you consider a map chi from the unit sphere of C0, so the unit sphere of C0 is the set of x in C0 which have norm 1. So if you consider a map from the unit sphere of C0 to K, where K is a compact metric space, and chi is one Lipschitz. Then for every positive epsilon, there exists some x in C0, choose C0. So here, what does it mean in this situation? I'm asking for a vector subspace of C0, which is linearly isometric to C0. So it's a copy in the sense of Banach spaces. Well, such that what? Such that the oscillation of chi on this, on the unit sphere of this subspace is at most epsilon. So look at this closely. Oh, I forgot to say, no, it is one Lipschitz, I said it. So look at this closely, and you will see that it is very similar to the indivisibility results we had for Q. So for Q, we had that for every coloring of Q with finitely many colors, you can find a subcopy on which it is constant. Here you cannot color the whole C0 because otherwise you could color a point by its norm. But if you restrict yourself to the unit sphere of C0, well, this chi acts like the coloring. Instead of a finite set of colors, you have a compact metric set of colors, and you know by experience, I guess, that in many cases, compactness is the right continuous version of finiteness. And finally, in the case of Q, you wanted to find a subcopy where it was constant. Here you want to find a subcopy where it is almost constant up to epsilon. You cannot remove this epsilon from the picture, otherwise it becomes false. So another theorem of the same kind.
Can you repeat just your observation about color in each point with its norm?
What I said is that imagine you don't just color the unit sphere, but the whole space. You could take for chi, like imagine that you take or even imagine you just color the ball, the unit ball. You take for k the interval 0, 1, and chi is the norm map. Well, if you consider a subspace, a slice of the ball, then all the norms from 0 to 1 will be attained. So the oscillation would be 1. So this wouldn't work. You see? So you have a theorem by Nguyen-Van T and Dauer in 2009, which say that exactly the same for the Eurison sphere this time. So for every chi from the Eurison sphere to a certain k, same, chi is one Lipschitz and k is compact. Then there exists a subcopy, an isometric subcopy of the Eurison sphere in itself, such that the oscillation of this chi restricted to x is at most epsilon. I forgot the for epsilon. You have the same, but it's not a Banach space, so of course you don't need to restrict yourself to a sphere. And I forgot to mention, but all the proofs of those two theorems rely on heavy Ramsey theory. Like for instance, this paper is 10 pages, and up to the middle of the last page, it's entirely discrete. It's entirely discrete combinatorics, and then he introduces Banach spaces only at the last page to prove this theorem. So it's really heavily combinatorial. I will give you a last one, which is by us. So theorem by Bice, myself, Hrubiczka, and Konechny. Same for the Banach space L infinity with just one twist. for every coloring chi from the unit sphere of the Banach space L infinity to k, once again, k is compact. Chi is one Lipschitz and weak star Borel. So let me explain this assumption. You probably know that for many Ramsey theorem, especially infinite dimensional Ramsey theorem, which is not the case here, but for many Ramsey theorem, when the set your coloring is uncountable, you need to have a definability assumption. Otherwise, you can construct bad colorings using the axiom of choice. So here it's exactly the case. You don't need this kind of assumption here and here because Lipschitzness implies continuity, which in the case where your space is a Polish space, which is the case here and here, it's a definability assumption. But the point is that L infinity and its unit sphere are non-separable, so they are not Polish. So having a continuous map or even Lipschitz doesn't count as a definability assumption. And actually we'll have counterexamples to the theorem built the usual way, where you don't suppose your map to be weak star Borel. So the right topology for definability here, just after, is the weak star topology. When you see L infinity as a dual of L1, this is a Polish topology. Yes, Paul?
So I have a question. So if you said weak star continuous, this would follow from Gauss's theorem, right?
No.
But
What?
L, I mean, C0 is, I mean, you know.
C0 is contained in L infinity, but there are some subcopies of is weak.
I said if you said weak star continuous, I didn't say this would follow.
Oh, weak star continuous.
Yes,
Oh.
continuous. But weak star Borel, I mean, weak star topology is compact on unit ball, right?
Uh-huh.
So Borel function is going to be continuous on dense G delta set. So you just need to enter that dense G delta set. I'm just asking what am I missing? Am I missing
Oh,
something?
I never realized that actually. Is it true that if you have this for a dense delta set, is it true that you always have?
You just need to enter it, right? And entering dense
Yeah.
delta set is not such a big deal.
Uh-huh.
Isn't non-separability still a problem? To get the dense G
No, weak star, but it's weak star.
Yeah, it's weird.
It's separate.
Oh, okay.
I should think of it. Maybe it's trivialized.
I'm probably missing something, but just it's my gut reaction that it should be that.
Maybe I should check.
Okay.
I will check. I will see. I would be surprised if it was so simple because I know that Stevo tried to prove it. Yeah, I know that Stevo tried to prove it for a while, but
Okay.
I will check. That's a good idea.
But is the combinatorics here different from the Gauss?
Completely different.
Why it's not
Yeah, completely different. Here in the case of Gauss theorem, it's his theorem for fin k. Yeah, it's fin k, and here is Carlson-Simpson.
Ah.
Okay.
But maybe what you say, I should check. That's an interesting question. Yeah, I will see after. Yeah, so I didn't even finish to state it, but it's the same. So if you consider this kind of colorings, then for every one Lipschitz and weak star Borel map, there exists some X copy of L infinity into itself, such that chi restricted to the unit sphere of X has oscillation at most epsilon. Yeah, so you have those three theorems, and well, a natural question would be indivisibility is when you color points. If now instead of coloring points you color tuples, can you get similar results, similar big Ramsey degree results? It's quite easy to see that if you color, for instance, at least pairs of points or tuples of points, you cannot get oscillation stability. But for instance, could you prove in the same way the existence of a bad coloring, like of an unavoidable coloring, which is in some sense the worst, and then you could prove a Ramsey theorem, a restricted Ramsey theorem relative to this coloring? Well, basically the rest of this talk is that yes, we can in this case, and in this case. A last motivation before I before I state our main results, will be a motivation coming from Banach space theory. So we have the following theorem by Odell and Schlumprecht. Which tells you that there exists some chi from the unisphere of L2, the Hilbert space, to the interval, let's say 0, 1. I'm not actually sure. I will put 0, 1/2 to be safe. But that means that that is surjective on every subcopy. So in particular, for L2, you don't have the same oscillation stability theorem as for C0. This problem actually is equivalent, like this theorem, it was an open problem for, I think, 30 years to know whether L2 had oscillation stability. The motivation is that oscillation stability for L2 is equivalent to another, would be equivalent to another result in Banach space theory, which would be that if you consider an isomorphic copy of L2, then you can find inside it almost isometric copy of L2 up to epsilon. So this is equivalent to oscillation stability. This oscillation stability is not true. So this other problem of finding isometric subcopies in isomorphic subcopies is not true either. But, well, there is several surprising things with these results. First of all, it's a quite long and technical paper published in ACTA. It was really solving a long-standing problem with a quite intricate proof that uses deep tools from Banach space theory. And usually when you prove a bad coloring result in combinatorics, well, it's pretty simple. So a big question is to know whether there is a simpler, let's say more traditionally combinatorial proof of these results. But also, well, same. You have a bad coloring. You have a coloring that doesn't stabilize. Do you have a big Ramsey degree? Can you find, in some sense, the worst of those colorings? And if you find the worst of those colorings, could you hope to prove a positive Ramsey theorem relative to this coloring? Well, this is one of the main goals of my life, but I don't hope to solve it before 10 years at least, and plus infinity is the most likely. But yeah, this also motivates you to develop a theory of big Ramsey degrees in the metric setting. So now I will state you to finish our main results. Now that you have all the motivations, because without the motivations, it wouldn't have been funny. So, is the third part, main results, and I will start with the horizon sphere. But you will see that L infinity works very similarly. So look at the oscillation stability result for the horizon sphere, which is just there. Your notion of colorings are one Lipschitz map with compact sets of colors. Oh, actually, something I forgot to tell you is that, of course, if it works for one Lipschitz maps, it works for every Lipschitz map. Actually, you can even prove that it works for uniformly continuous maps by an easy change of scale argument. But I stated it for one Lipschitz maps. All those three theorems, I stated them for one Lipschitz maps because it's the way, like in the results I will state now, one Lipschitz maps are necessary. So our colorings will be one Lipschitz maps with compact metric sets of color. So a coloring by definition, is a map chi from S to K, one Lipschitz K compact metric. And maybe you have realized that in the definition of big Ramsey degrees, the ordering on omega has a certain role to play. We say that the big Ramsey degree is the smallest number of colors for which you can always reduce to this number of colors. So if you wanted to do things the same way, you would need an ordering on compact metric spaces. And actually there is one. I will just give it now because this is what will justify that I want my maps to be one Lipschitz. So order, but we won't need it in the statement of the results. So order on compact metric spaces you say that K is less than or equal to L if there exists some F from L to K, which is onto, and one Lipschitz. This, not a very difficult result. This is a partial ordering, but the main issue is that, well, for the definition of big Ramsey degrees, you want to say the smallest, but here it's not even well-founded. It's not well-founded, it's not total, so you cannot really work with that. And so the solution we chose is to work with analogs of big Ramsey coloring, it said. Actually, we have four non-equivalent candidate definitions for big Ramsey degrees in the metric settings, which in the discrete setting are all equivalent to each other. And the one we chose is the strongest one, the most difficult to achieve, because we saw that it works on examples. And this strongest definition is the existence of a universal and unavoidable coloring. So I should define what is a universal and unavoidable coloring of the Eurisson sphere. The coloring chi is said to be unavoidable if for every subcopy of S, so remember the discrete case, we wanted that on every subcopy the coloring reaches all the colors. This is not something you can ask, you can require in the metric case, you can only require density. So the right notion of surjectivity here is density. So it is unavoidable if for every X, the image of X by the coloring is dense in your compact K. And now you say that your coloring is universal. If what happens, well, in the discrete case, the Sierpinski coloring was universal, and the result was that you could factor any other coloring on a subcopy. Now, if you look, so this was a positive Ramsey result, and now if you look at positive Ramsey results that we know in the metric case, which are oscillation stability results, you see that you cannot always reduce to one color. There is some epsilon approximation which is needed. So here it will be the same. For defining universality, I won't require factorization, but factorization only up to epsilon. So it is universal if for every other coloring from S to L, there exists a subcopy of S in itself, such that, well, I will draw the diagram. here you have your subcopy X, you have your universal coloring chi, you have your arbitrary coloring psi to L, and what you require is that you can factor what?
For every epsilon in there?
Oh, I forgot my for every epsilon. For every epsilon, yes. For every psi coloring and for every epsilon, there exists a subcopy such that you can find a factoring map which is itself one Lipschitz, such that this diagram commutes up to epsilon, meaning that so there exists some f from k to L, which is one Lipschitz, such that it factors up to epsilon for the uniform distance. So that is for every x in, oh no, okay, I made a mistake. But I will correct it quickly. You're not coloring S here. You know that if you're coloring S, you have oscillation stability. So it's not whenever you color S that something interesting happens. It's when this time you want to color embeddings of finite structures into S. So it's more like I will fix a finite metric space of diameter at most 1, and I don't color S, I color the embeddings of A to X, of course. Exactly as in the discrete case, I was coloring the embeddings of a two-element set in Q. So here I color the embeddings of A in S with K colors. Of course, chi is one Lipschitz, so you need to put a metric on M by S. You will put the uniform metric of embeddings from A to S. And same, now saying that my coloring is unavoidable means that for every subcopy of S, not chi of X, but chi of the embeddings of A in X is dense. And here it's similar. For every copy, for every other coloring of M A X to L, there is a subcopy such that your arbitrary coloring factors up to epsilon through your universal coloring on this subcopy, but actually on the embeddings of A to this subcopy. There exists X. So let me summarize. It is universal if for every other coloring and for every epsilon there exists some subcopy and there exists some one Lipschitz factoring map, such that you have this factorization, meaning that for every U embedding of A in X, you have that the distance between f of chi of U and psi of U is at most epsilon. This is an unavoidable, this is a universal coloring. And finally, you say that it is a big Ramsey coloring if it is both universal and unavoidable. So chi is a big Ramsey coloring if it is both universal and unavoidable. And now the theorem. is that so fix A, a finite metric space for which you want to have a big Ramsey degree in S. Then there exists chi from MAS to K, a big Ramsey coloring. But the theorem is not finished because remember Q and remember the Sierpinski coloring. The Sierpinski coloring was not unique because it was defined from an arbitrary well ordering of Q. Now if you change the well ordering, you change the coloring. But what was unique is that it had two colors. Here it will be exactly the same. The coloring is not unique. It's actually defined from a certain curve which is dense in the iridescent sphere. But the set of colors is unique. So moreover, K, let's call it K, is unique up to isometry. And
Can
since
you say what is K?
K is the set of colors.
No, I mean, can you tell us what is the set?
It would take 20 minutes.
Never mind, okay.
I can tell you separately after.
Okay.
It's some nice thing, but not easy to define. So K is unique up to isometry. Well, definition, it is, we call it.
The K depends on A.
It depends just on A, yeah. It is called the big Ramsey degree of A in S. So in the discrete setting, given a structure, you could associate to this structure a sequence of numerical invariants, which for each finite substructure you had a numerical invariant, which was a number of color. Now your invariants are not only quantitative, they are compact metric spaces, they have a geometry. And you have a family of invariants for every finite substructure. So now let me just ask you a question. Do you see what is BRD of points in S?
Single point.
Yeah, if you color singletons.
Oh, well, hold on. Let's. Well, isn't that the Lionel and Sal?
Yeah.
Yes.
Yes, exactly. So it will be a singleton. Actually, this theorem is equivalent to say that the BRD of singletons in S is a singleton because, well, you have only one coloring taking values into a singleton. It's a constant coloring. Saying that it's unavoidable is obvious. Saying that it is universal exactly means that every other coloring factors through a constant map up to epsilon, but factoring up through a constant map up to epsilon just means being constant up to epsilon. So having oscillation at most epsilon, which is exactly this. So in the case of singleton, it is a point, but in the case where you color more complex structures, it is not a singleton. It is some much more complex compact metric space
So in the
that I
case
won't
of
describe.
pairs,
What?
Exactly.
is it easy to describe in the case of pairs?
No, it's the same for every. So basically, I can more or less explain you like how it works quickly, but without details. Imagine that you are points of the iridescent sphere, and I'm a visitor. I will go along a curve which will be dense in the whole iridescent sphere, and I take 2 points, for instance, and along my trip, I will be able to measure my distance to both of you. If I know that I'm distance 2 of you and 3 of you, then by the triangle inequality, I know that the distance between the two of you is at least 1 and at most 5. Along my trip, I will continue at each point. It's a continuous trip to measure my distance to both of you, and I will get more and more information. At each time, I will get a lower bound and an upper bound. At the beginning of my trip, my lower bound will be 0, my upper bound will be 1 because the big Ramsey degree of the Euryson sphere, because the Euryson sphere has diameter 1. And at the end, since I am dense, I will pass very close to each of you. So my estimation will tend to the actual distance. Basically, the color I will give to your pair is this recording of all this information I measured during my trip. And so the big Ramsey degree itself is the compact set of all possible towers of information of this form. It would be a bit long to define, but basically that's it. And same for 3 points, same for 4 points. Yeah.
And for singletons, there's just one.
Yeah, for singletons there is just one. So there is just one. There is just one last thing I want to tell you, is that as a corollary, the isometry group of the Euryson sphere has a unique metrizable universal completion flow exactly as in the discrete case. You can deduce this dynamical statement from the big Ramsey degree statement. So now you can do exactly the same with L infinity. I won't state you the theorem again because it's exactly the same. In the case of L infinity, there is just two things you need to change. Your colorings will be defined on the unit sphere of L infinity. Your subcopies will be linear isometric subcopies of L infinity in itself. And your colorings, you will require them to be Borel for the weak star topology. And apart from that, well, just take the results, like the same definition of unavoidable, same definition of universal. You get exactly the same theorem with, of course, other compacts, other invariants, but you have the same result. And same, the description actually of the compacts for L infinity is a bit simpler. If you color k points in L infinity, k points of the unit sphere, then the kind of colors you will get, one color will be what we call a pumpkin. It's a convex, compact, and symmetric set in the d-dimensional, in the k-dimensional cube, which grows from a seed up to touching all the faces of the cube. And the recording of its growth is a color. Same, the big Ramsey degree of coloring d tuples in L infinity is the set of all those possible growth evolutions. That's all I wanted to say. Thank you for your attention.
So I have a question. Oh, okay.